Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing the evolution of olefin polymerization catalyst, and in that way we have drifted quite a bit. We started with Ziegler-Natta heterogeneous titanium zirconium group 4 transition metal based catalyst, which are multi-site catalyst with extremely high activity for ethylene homopolymerization as well as propylene homopolymerization, and then gradually drifted towards metal group 4 transition metal based metallocene type single site catalyst, which were extremely well behaved in terms of being able to polymerize homopolymerize ethylene as well as propylene, and also show extremely high activity depending on the modification of the transition metal group 4 metallocene catalyst. And then subsequently we went into towards looking for copolymerization of various kinds of olefinic monomer, and subsequently copolymerization with monomer bearing functional groups. Now, in that aspect too, we had moved over from group 4 transition metal catalyst titanium, zirconium, hafnium, and then went on to discuss about other metals, for example, lanthanide based olefin polymerization catalyst, and which we had seen that even though they can polymerize olefins, but they cannot compare in terms of activity with respect to group 4 transition metals. Now, in this comparison of looking for other non-group transition metal matching up to the activity of the group 4 transition metal, contribution by Brookhart and Gibson was discussed in the last lecture, in which iron catalyst, which is a non-group 4 transition metal, showed extremely high activity in terms of olefin polymerization, and it could give a range of products depending on the substituents going from oligomer all the way to the polymer, and this was a tremendous discovery in terms of putting iron back into the polymerization map of in olefin polymerization, and iron being the most abundant metal on the earth, being cheap and economically viable. This is a great news for people who are exploring iron based catalysis. So, in the last class we had seen this the catalyst which is drawn over here. Ethylene, when R equals methyl and R dash equals hydrogen, oligomer alpha olefin C10 to C20 fraction. Produce high density polyethylene. Now, this and the activity comparable to Ziegler-Natta catalyst. So, this is a great news in terms of the chemistry and in terms of developing iron as a catalyst. This in short is designated by N FeCl2 slash MaO catalyst. Now, in this the interesting thing is that in this the chemistry that chain termination competes with chain growth, and that is shown over here. So, N Fe plus polymer with ethylene gives NNN Fe polymer and ethylene with iron in the plus state. Then this will come and insert, which will then give N Fe polymer with Fe plus. So, this is a chain growth, whereas this has 3 chain termination pathways as well. So, this is a chain growth reaction, and it has 3 chain termination pathways as is shown here. The first one is this will bind to the ethylene, and one can have N iron polymer bound to ethylene. It has a hydrogen, and it can beta hydrogen can eliminate and become a iron hydride, and that can insert into the thing. So, that can eliminate propene, this moiety, and then it can give N Fe plus hydrogen, which can again undergo ethylene to give chain growth. Chain growth. So, this mechanism is sort of a chain termination mechanism, but giving rise to chain growth. There are other possibilities as well, which is shown here. So, this with Me3Al trimethyl aluminum or MaO would give this complex N Fe plus polymer Al methyl. So, in this case what this is that a trifluoro tricycle aluminum unit. This is in methyl is interacting with iron, and as a result there is a chain transfer that happens. Chain transfer, and this kicks out polymer Me2, and this methyl gets transferred to iron from aluminum, and the unit which goes out is this. As a result, what stays behind on the catalyst is Fe plus methyl, and that with ethylene again goes to chain growth. And so, what is interesting over here, that here we have chain growth which leads to the growth of the polymer chain, and here we have this chain termination mechanisms. This is mechanism number 1, this is mechanism number 2, both also leading to chain growth. So, as a result the catalyst gives very high yield high molecular weight polymers, and then this is not the second one, there is also a third one which is a possible third pathway chain termination, and that is given by this. So, this gives N Fe plus hydrogen polymer that undergoes associative exchange and as a result what happens is olefin comes in and propane goes out, as is shown, to give N Fe plus hydrogen in this, and this in presence of olefin again gives chain growth. So, what we have over here are 3 chain termination pathways. This is pathway number 1, this is pathway 2 and pathway 3. All the termination pathway eventually in presence of olefin giving chain growth, and this is in addition to the normal chain growth pathway. So, this is a wonderful catalyst which, because of these reasons, could match up to the activity of that Ziegler-Navier system and could carry out polymerization, and we have seen that how chain growth helped in producing longer catalyst. Now, we have moved from we move and go beyond iron, and we move to nickel from here, and we had seen that how the story sort of started with nickel, how the story sort of started with nickel in terms of the nickel effect, which sort of helped in discovery of the Ziegler-Navier catalyst, and then it went back a complete circle from nickel to titanium, zirconium to lanthanum to iron, and then it again goes back to nickel, and now we are going to be talking about how nickel can be used for producing polyolefin polymers, and the credit goes to Professor Maurice Bruchart, who used a bulky system of the type shown that could produce polymer. And the ligand are of two types. One is this, or this. So, this is a bulky system, and we can in short we can designate this as this ligand. What this ligand does is that in its nickel complex, in ether at minus 78 degrees centigrade in presence of H protonating agent Pf4, it eliminates methane to give this compound, and then just the ether solvent ethylated Ar4. So, this is the counter ion, and with propene, it could give polypropylene of N, and the same he could also start, instead of the methyl he could also start it from the nickel dibromide precursor using MaO 1000 equivalent toluene with isopropane, or it can or can be hydrogen, methyl, butyl. It could also produce the same pathway. So, this is one can think of this as pathway 1, and this is pathway 2. The polymer produced by pathway 1 are high branching, branching, whereas polymers produced in pathway 2 gives a high grade linear polymer. And one can sort of control the grades of the polymer depending on the conditions used or pathway follows. So, in one case one can get high grade linear polymer, in another case one can case highly branched polymer. So, this was a nice work where Brookhart also put nickel in the map for making polymers, because nickel the whole business started off with nickel being in the nickel effect, setting it off, and then nickel known in shop where it was mainly used for oligomerization catalyst. It is however, Professor Brookhart's work which made nickel to come into the map of olefin polymerization, and it also convincingly demonstrated that how nickel can be used even to make polymers. And nickel being a late transition metal, it has a propensity to chain walk during the polymerization, and that is what is explained by branching that is observed. Now, continuing further, a nice work by Professor Bazan took nickel to much higher heights, where he used two catalysts working in tandem to produce high molecular with polypropylene. So, this is a property which uses two catalyst transition metal, one is nickel and another is titanium, to produce a polymer in a tandem fashion, and this is nicely demonstrated illustrated over here. So, Bazan in 2000 showed used nickel in combination with constraint geometry titanium catalyst to produce polyethylene copolymer of 1 butene. The good thing is that this is a copolymer process with only one monomer, which is ethylene. So, this is a kind of a phenomenal work. Let me illustrate why. First of all, that it uses two catalysts, one is nickel, another is constraint geometry titanium catalyst, two catalysts producing a copolymer of ethylene and 1 butene. But the catch is that there is only one monomer, which is ethylene. So, one catalyst is used first to convert ethylene to butene, and then the second catalyst, the first catalyst is nickel, which used ethylene to butene, and then the second catalyst titanium sort of polymerizes the butene and ethylene to give this copolymer ethylene CO1 butene. So, this is a beautiful elegant demonstration of organometallic chemistry. It also shows how clear thinking can lead to wonderful catalyst development, where two catalysts are made to work in a tandem. Let me illustrate this more specifically with the catalysts that were being used. The first catalyst is obviously a nickel catalyst, which is of the formula this. This is a nickel allyl complex that is activated with boron C6F5 whole 3. This the catalyst converts ethylene to 1 butene. Now, this 1 butene then reacts with maybe I will do it with a different color. 1 butane then reacts with another molecule of ethylene and undergoes copolymerization using a constrained geometry catalyst. Titanium methyl plus, and this is a boron C6F5 whole 3 minus. So, it does this does a copolymerization to produce M N LLDP. So, the good thing is that this in this case 2 catalyst titanium and 2 catalyst titanium and nickel work in tandem. Tandem in same medium on single substrate, on one substrate which is ethylene to produce LLDP. Which is this. So, this is a tremendous demonstration of the capabilities of organometallic chemistry, in which this LLDP was produced, and depending on the variation of the conditions, one can control the chain length and the molecular weight, and depending on the incorporation extent also of 2 different by varying the nickel to titanium ratio. It should also be mentioned that these 2 catalysts, nickel and titanium, are not interfering with each other. So, with this we come to the end of today's lecture, where we had seen the catalyst development from iron Gibson's catalyst to Bruckhart's nickel, the focus shifting from iron to nickel, and what it says that there are a lot of chemistry even left with the other transition metal other than non group 4 transition metal, and in this case nickel and iron indeed showed did prove their strength in terms of doing wonderful chemistry, and the last example by Bazan where tandem reaction between nickel and the constrained geometry titanium group 4 catalyst took polymerization to a different level. So, with this we come to an end of today's lecture. We are going to dwell a bit more on non-metallous non group 4 transition metals when we take up the topic in more detail in the next class. Till then, thank you and goodbye.